All right, the homework on thin film interference and interferometers is probably one of the harder ones in the optics section, so I'm going to spend a little more time than I normally would working example problems. All right, our first example problem is thin film interference. A part of a soap bubble has a thickness of 1.11 microns. What wavelengths of visible light will have a reflection maximum from the bubble? Assume that the soap film has an index of refraction of 1.33. Now, of course, if you read about dispersion, you know that the index of refraction actually changes with wavelength in a given material. For this problem, we're going to assume that's negligible, that the index of refraction is just 1.33 for all the wavelengths we're interested in. All right, now 1.11 microns is the thickness of our film. 1.11 microns. Microns is just another name for micrometers. All right. Now, a micrometer, as you'll recall, is just 10 to the minus 6 meters. So this is 1.11 times 10 to the minus 6 meters. All right? But it turns out for this problem, I like to think of wavelength in terms of nanometers. It just makes me happy. So let's think of our thickness also in terms of nanometers. So 1.11 micrometers is also 1,110 nanometers. All right. Now, we're looking for wavelengths of visible light that have a reflection maximum. What does that mean? What are the wavelengths of visible light? Well, it turns out your eye does not suddenly stop seeing light at a specific wavelength. It's kind of a gradual cutoff. So we're going to use a very typical range that people use, which is I'm going to assume that anything from 450 nanometers to 750 nanometers is visible. All right? That means that the purple laser pointers at 4 or 5 nanometers are invisible. But you can see them, right? It's just that your eye response is much lower at that wavelength than within this range. In fact, purple laser pointers can be very dangerous because they're a lot brighter than they look. Your eye does not respond to them very well, so be careful with them. Anyway, so we're looking for maximums of reflection in that range for a soap film with this thickness. Now, how do I find what the maxima are? What wavelengths have a reflection maxima? Well, let's look at our soap film. I've got some light coming in near normal incidence. I'm going to draw it at a slight angle, though, so we can see the different reflections. But if I don't say the angle coming in with thin film interference, just assume I mean normal incidence. All right, the light hits the first surface of our film, and it reflects. We're going from air to the film, so that's low index to high index. That means we get a 180-degree phase shift for this reflection. Then some of the light goes down, reflects off of this surface, and comes back, and transmits and comes out, and then so forth, right? We get lots of reflections. But we're just going to look at these first two. If they're in phase, I have a bright reflection. Now this reflection down here, it goes from high index to low index, so there is no 180-degree phase shift. So if I want these two beams to be in phase with each other to make a bright reflection, that means that this path length needs to get this beam back in phase with this one that had its phase jump by 180 degrees when it reflected. All right, the transmitted beam never has a phase shift. All right, so that means my path length down and back, which is 2 times t, I want that to be equal to a half integer number of wavelengths. I want it to be an integer plus 1/2 times the wavelength of light, but we want the wavelength of light in this medium. So it's the wavelength of light in vacuum divided by the index of refraction. Now the wavelength we're looking for, when I ask for a wavelength, I usually mean, unless I say something specifically, I mean the wavelength in vacuum. So lambda is going to be the wavelength in vacuum, but how much of a phase shift you get by traveling this distance depends on the wavelength in the medium, so we have to divide that by n in our equation. If I solve this for wavelength, I'm going to find then that the wavelength is 2t times the index of refraction divided by m plus 1/2. Now the multiple wavelengths are possible because I can plug in different values for m. What are valid values for m? Well, they have to be integers, and it turns out they have to be non-negative. If I put in -1, I'm going to get a negative thickness. That doesn't make any sense for a given wavelength, all right? So 0 is good, 1 is good, all non-negative integers are good. So let's go to Python now, and we'll plug in some numbers, all right? So the wavelength is going to be 2 times the thickness. I'm going to put it in nanometers because it's the only thing with units in the whole problem, and I want to see my wavelengths in nanometers. So let's just put in 1110 nanometers times the index of refraction, which is 1.33, and then we're going to divide by m plus 1/2. Let's start with m equals 0 and see what we get. Okay, that is way off. That's not even close to being in the visible range. So let's try another number. How about 5? Okay, 5 works. That's within our range. How about 6? 6 works. 7 is outside of our range, so that's no good. 5 and 6 are good. Let's go below 5. How about 4? 4 works. How about 3? 3 is outside of our visible range. So it looks like the wavelengths we got that are within the visible range are 454, so let's write that down, 454 nanometers. Then the next biggest one was 537 nanometers. 537 nanometers. And the last one in the visible range was 656 nanometers. 656 nanometers. So those are the wavelengths which will give us a reflection maxima on this particular film. Okay, on to our next problem. Anti-reflective coatings. A lens is made of glass with an index of refraction of 1.51 at a wavelength of 500 nanometers. So the index of refraction is a function of wavelength, and I'm just saying at 500 nanometers the index of refraction is 1.51. We want to put a thin film of magnesium fluoride, which has an index of 1.39, on the lens to reduce reflections at the surface. What is the minimum thickness which will produce a reflection minimum at 500 nanometers? So 1.51, 1.39. Let's remember that. So what we've got is this film with an index of refraction of 1.39, and it's on top of glass with an index of refraction of 1.51, and the air has an index of refraction pretty close to 1. Alright, so we want light with a wavelength of 500 nanometers to reflect off of here and have a reflection minimum. So our wavelength is 500 nanometers. We come in, we reflect off of the first surface of our film. We're going from low to high index, so I'm going to get 180 degree phase shift. Some of the light transmits, comes down here, it's going to reflect off of this surface. When I reflect off of here, I'm going from a lower to a higher index again, so I get 180 degree phase shift on this one as well. Alright? So unlike the previous problem, now I get two 180 degree phase shifts. However, unlike the previous problem, I am looking for a minimum. I want a minimum reflection, not a maximum. So these two are naturally inclined to be in phase with each other. They both get 180 degree phase shifts. So I want this path length to get them out of phase, which means, once again, I want a half integer number of wavelengths in this path. So 2 times t is equal to an integer plus 1/2 times the wavelength, and again we want the wavelength in the medium, so divided by n, where n is going to be the index of refraction of the magnesium fluoride. Alright, and my pen's doing something funny, I apologize. Alright, so we wanted to get the minimum thickness that will give us a reflection minimum, and that happens when m is equal to 0. So let's just set m equal to 0, and we get 1/2 lambda over n. Solving this for the thickness, t is equal to lambda over 4n. Alright, and we just plug in our numbers now. 500 nanometers divided by 4 times 1.39, and I'll let you plug that into your calculator. That's the thickness you need. This is what's known as a quarter wavelength coating. This is a very common coating. Take lens, put a quarter wavelength of magnesium fluoride in order to minimize reflections for light entering your lens. More expensive lenses will have multi-layer coatings that reduce reflections even more. Okay, our next problem is a problem with Newton's rings. Newton's rings use interference to figure out if a lens is shaped properly. So imagine I place a plano concave lens on a plate of glass as shown below, down here. Alright? Now, I shine light with a wavelength of 633 nanometers onto the lens at normal incidence, making a pattern of light and dark rings. Why do I get light and dark rings? The thickness changes, alright? And so at some thicknesses, alright, this is an exaggerated picture, so we're going to assume that the lens is pretty flat over the region we're interested in. The light comes down, it's just basically reflecting back and forth, and for some thicknesses, 633 nanometers will have a maximum in reflection, and some it'll have a minimum in reflection. So I get light and dark rings. Why rings? Because if I have a spot over here where it doesn't reflect well, there's also a spot over here on the other side where it doesn't reflect well, and all the way around my cylindrical lens. All right? So I shine light with a wavelength of 633 nanometers onto the lens at normal incidence, making a pattern of light and dark rings. The very center is a dark ring. The sixth dark ring from the center, not counting the spot at the center, has a radius of 1 centimeter. What is the radius of curvature of the concave side of the lens? All right, so when the light comes in and hits this surface, I'm going from, we don't care what happens up here. This is our thin film down here, all right? This is a thick film up here. But when I hit the surface, I'm going from high index to low index, which means I do not get a 180 degree phase shift. But then when I go from air back into glass at the bottom, I do get a 180 degree phase shift, and so my light's coming up here. All right, now it's telling us we're thinking about dark rings in this problem. It says the center's a dark ring, I'm looking at dark rings. So a dark ring is what I would get if there was no space between these two. All right? So if I travel some distance down and up again, I want that distance to be an integer number of wavelengths. So to get a reflection minimum, a dark ring, I want 2 times the thickness, that's the distance I traveled down and back in this air gap. I want that to be equal now to an integer number of wavelengths, right? These two are out of phase because of this reflection getting a 180 degree phase shift. We want them to stay out of phase, so we want an integer number of wavelengths in that path, all right? Now, I'm not dividing by n because where the traveling is happening is here in air, not in the glass, right? So our film is now an air film. Its index of refraction is 1, so I'm going to divide this by 1, all right? So these are the thicknesses which will, for any given m, I plug in my wavelength and I can tell you a bunch of different thicknesses that will produce dark rings. In the very center, let's say the very center has a distance t naught. So 2 times t naught, we've got a dark spot in the center, all right, a dark ring in the center. So we know that this satisfies the equation for some integer m. Let's call that m naught. So for some integer m naught, when I plug in my 633 nanometers, I will get a dark fringe because T naught is going to, and that M naught are going to satisfy this, all right? But as I go out, the thickness changes, and I get dark fringes for different thicknesses when I can satisfy this equation with a different integer, all right? So right here in the center, when M is equal to M naught, I get a fringe. But as I move out, the thickness goes down. But at some point, as the thickness goes down enough, I can satisfy this equation by making M go down by 1, right? And if I go down again, I can find another point where the thickness satisfies this equation by bringing M down by 2. And I told you, after we go out 1 centimeter, I've hit the 1, 2, 3, 4, 5, 6th fringe, all right? The 6th dark line. So that means the thickness out here, once I've gone out 1 centimeter, is going to be, we'll call that thickness 1 for 1 centimeter. How's that, all right? That's going to equal m naught minus 6 times lambda, because as I move out different fringes, m goes down, all right? So I know if I know the thickness at the center, that's equal to m naught times lambda, right? And the thickness out here times 2 is equal to m naught minus 6 times lambda, all right? So that's my basic equation. So let's write them down again. Here are my basic equations. 2 times the thickness at the center is going to be equal to some integer times lambda, times the wavelength. 2 times the thickness out 1 centimeter away off to the side, that's going to equal m naught minus 6 times the wavelength, all right? So I've got this surface right here. This surface is part of a sphere. So let's draw that sphere now, all right? I've got the sphere. I want to find the radius of curvature of that sphere, all right? Well, here's my lens. Here's a little piece of that sphere, and here's the glass plate we're going into. I know that something about this distance, and I know if I go over 1 centimeter, all right? So this distance right here is 1 centimeter. Let's call it capital D. How's that, all right? And this distance right here is the radius of curvature of the lens. And this distance right here is T naught, all right? Okay, so we come over here 1 centimeter. Here's T naught, I come over 1 centimeter. That's not T naught. Well, okay. This distance right here is the difference between, maybe my lens goes down here, right? So this distance is T naught, but this distance right here is the difference between T naught and the thickness out at 1 centimeter. So I'm going to call this distance right here, let's call it S. S is going to be equal to the thickness at the center minus the thickness at 1 centimeter off this way. And D is going to be our 1 centimeter, right? And so what we have to do is we have to find R, all right? So if I look at this guy right here, I've got a triangle here, I've got a right triangle, and I can use Pythagorean's theorem, all right? Because this distance right here, that distance is R minus S, right? And if I take R minus S and square it, and add it to D squared, that's going to equal the hypotenuse squared, right? But the hypotenuse is just R squared, right? So I use Pythagorean's theorem. This side squared plus this side squared is this side squared. This right here is how far we went out to find the 6th fringe. This distance right here is the thickness difference between the thickness at the center and the thickness out where I found the 6th fringe. So that's T naught minus T1 centimeters. We call that S, right? And this distance is just R minus that distance S. So now I just have to solve this equation for R. D is known. What is S? S is the difference between these two. Oh, but if I take the difference between these two, I will find that S is equal to, let's divide these both by 2. How's that? Divide that by 2. Now if I take this minus this, that's S. So this minus this is going to be m naught lambda over 2 minus m naught minus 6 lambda over 2. And that cancels with that, and I find then that S is just equal to 6 lambda over 2. The minus signs then cancel. 6 lambda over 2, or 3 lambda. All right? So S is 3 lambda. I'm given the wavelength. So R minus 3 lambda squared plus D squared equals R squared. And all I have to do is solve this for R now, right? Because lambda is given and D is given. All right? And so if I multiply this out, on this side I get R squared minus 6 R lambda plus 9 lambda squared plus D squared is equal to R squared. How convenient. My R squareds cancel, and I can take my R to the other side, and I get 6 R lambda. Right, I take this over to the other side, and I get this, and what's left is, that's equal to 9 lambda squared plus D squared, right? Divide by 6 lambda, and I'll find that R is equal to 9 lambda squared plus D squared over 6 lambda. All right, I stopped for a minute. Do my units work? Yes, they do. I've got meters squared over meters and gives me meters. Does it make sense? Anyway, you think about this. If D were bigger, if I had to go out further to get those fringes, that means that the thickness isn't changing as fast, and that's a bigger circle, so it makes sense. If D is bigger, then I get a bigger radius of curvature. That makes sense. What about the wavelength? If the wavelength is bigger, this is a little complicated because we have kind of two terms here, one that goes as wavelength and one that goes 1 over wavelength. So maybe it's a little harder to build intuition. But anyway, the one thing that was easy to check made it look like our answer's doing the right thing. The units work out, so maybe we got the right answer, and all we have to do now is plug in numbers, and I'll leave plugging the numbers in to you. All right, there's how we work the problem to find the radius of curvature of that surface on our lens. Okay, our next problem is on interferometry. A Michelson-Morley interferometer has a glass cell which is 2 centimeters long and 1 arm. The mirrors are adjusted so that the center of the beam coming out of the interferometer is black, devoid of light. We then slowly pump air out of the cell until we achieve a near-perfect vacuum. How many times will the light at the center of the output go bright and then black again? The index of refraction for air in the room is 1.00027772. All right, so the index of refraction for the air is 1.00027772, and our cell is 2 centimeters long. All right, we're going to write this down because now I want to use variables. People who plug numbers in too fast end up making mistakes. That's what I've found. So we've got our Michelson-Morley interferometer, a laser comes in, and the wavelength is 633 nanometers. So a 633 nanometer laser beam comes in, hits this beam splitter, gets reflected off of mirrors, they come back. But one arm of the interferometer has a cell in where I can suck all of the air out. Alright? So how does that change the phase of the relative phase of these two beams? Initially, before we start sucking air out, we adjust these mirrors so that I'm getting a dark spot here in the middle. Alright? That means these two beams are 180 degrees out of phase. Alright? And then, if I do anything to change the phase of one beam relative to the other, that will change how much light comes out. For example, if I move this mirror by 1/4 of a wavelength, that shifts, right? The light goes out and back, so that shifts kind of the path length by 1/2 a wavelength. So now this is going to be shifted in phase with the other beam, and I'll get a bright spot in the middle, right? But I'm not going to move the mirror. What I'm going to do is I'm going to change the index of refraction of the stuff inside the cell. I'm going to suck the air out. Alright, so what we're going to do is we're going to say, look, as we travel through this cell, how much does the phase of the light change by? Well, if you travel one wavelength, that changes the phase by 2 pi, right? So the phase shift we get is going to be 2 pi times L divided by lambda. Every wavelength that we travel will shift the phase by 2 pi. Except, remember, the wavelength we have to use is the wavelength in the medium. So that's the wavelength in vacuum divided by the index of refraction. So initially when we start off, the light's getting that much phase as it goes through. But it also gets that phase as it comes back, right? We're going to go through 2 times. So let's multiply this by 2. So this is the phase shift the light gets because it's passing through this cell. Alright? But if I suck the air out, that phase shift is going to change. So initially when we have air in there, let's call that air in there. When I suck the air out, now I've got vacuum, I'm still going to get a phase shift, right? Because light travels, and it's still going to be 2 pi phase shifts for every wavelength times 2 because I passed through it twice. But now the index of refraction is 1. So I'm going to get less phase shift because the wavelength is longer as I pass through the cell in vacuum than what it is with air. Alright? Very, very slightly though, because the index of refraction for air is very close to 1. So how much does my phase change for this beam when I suck the air out? Well, it's going to be what I had with air minus what I have with vacuum. Alright? And with air I have 4 pi NL over lambda. And with vacuum I have 4 pi L over lambda, right? N is 1 for my vacuum. Alright? Which means that this is just going to be 4 pi L over lambda N minus 1. That's how much the phase changes. Now N is very small compared, N is very close to 1 for air, right? So this phase shift, the amount that the phase of this beam changes when we suck the air out, it's going to be really small, right? But that's the beauty of an interferometer. It's very powerful. It can measure very small changes in phase. How many dark fringes are we going to go through? Every time the phase of this beam changes by 2 pi, we're going to go from one dark fringe to the next dark fringe. So the number of dark fringes we go through is just going to be this thing divided by 2 pi. Alright? Every 2 pi, every 360 degrees, I go from one dark fringe to the next dark fringe. Alright? But this is just, if I take this and divide by 2 pi, that's just going to be 2L over lambda N minus 1. Alright? So now we can plug things in to Python. Alright? So we have 2 times L. L is 2 centimeters. So 2 times 10 to the minus 2 times N minus 1 is 0.0002772. And then I divide that by my wavelength, which is 633 times 10 to the minus 9 meters. And I get 17.5. So 17.5 dark fringes. So it'll go from a dark fringe to another dark fringe 17 times and then go halfway. So it'll end up on a bright fringe as I pump the air out. So there's my answer, and this shows that interferometers can be extremely sensitive. Changing the index of refraction a tiny, tiny bit, we get 17.5 fringes, which is very easy to measure. And we're done.